Hello friends, welcome to the class of Differential Calculus. We are studying Successive Differentiation, and today in this lecture we shall study a very important theorem which is known as Leibniz theorem. So theorem is useful to find nth derivative of product of two functions. So before considering the theorem and its proof, we shall have some revision of binomial coefficients or formulae from combinations. So we have studied this earlier. Now we know this symbol or the formula n choose r or NCR. This may also be written as n choose r, or sometimes it may also be written in this form, but we will use this notation. The formula we know is n factorial divided by n minus r factorial of n minus r into r factorial. So these are exactly the number of ways that r objects are chosen from n objects, and therefore the symbol is called or read as n choose r or n combination r, and that is n factorial divided by n minus r factorial into r factorial, or factorial of n minus r into factorial of r. So this is the formula for binomial coefficient, and from this formula we can see what will be n choose 0 or nc0, and that means how many ways 0 objects can be selected from n objects, and by this direct formula we can see it is equal to 1, and also this is n choose n, and it is also equal to 1. Further, this may also be written in this form n plus 1 choose n plus 1. If this the total objects and selected objects are equal, then the value is 1, and if also nc0 is also 1, or n plus 1 choose 0 is also 1. And one more relation we shall require, and that is n choose r minus 1 plus n choose r, and this is equal to n plus 1 choose r. NCR minus 1 plus NCR is equal to n plus 1 CR, or n plus 1 choose R. So these are some formulae we have to use in the theorem, Leibniz theorem, to prove the Leibniz theorem. Now we shall write the statement of Leibniz theorem. The theorem statement is if. So this is the theorem used for obtaining nth derivative of product of two functions. Leibniz is name of mathematician, and he was famous mathematician who actually discovered this branch of differential calculus, or the branch of calculus discovered by Leibniz. Independently, Newton also discovered the same branch of calculus. Now we shall see the statement of Leibniz theorem. If u and v are functions of x possessing or having the nth derivative, or having the derivative of nth order, derivatives of nth order, because we are differentiating n times, then the derivative of their product, we will use our usual notation. This is the notation we are using for nth derivative of u into v. This is equal to, in terms of binomial coefficient, we shall write n choose 0 un into v. Un means nth derivative of u, plus n choose 1 un minus 1. Decrease the order of the derivative of u, increase the order of derivative of v, plus n choose 2 n minus second derivative of u and second derivative of v, that is v2, plus so on. And in general, the general term is n choose r, n minus rth derivative, from this you can observe, and into rth derivative of v plus so on. And the last term will be, last binomial coefficient is n c n, or n choose n u v n, nth derivative of v. So this is the statement of Leibniz theorem. Now you may observe nth derivative of u into v is, there are three terms, three parts in each term. First is binomial coefficient, second is the derivative of u, and third is v, or derivative of v. In the first term, it is see the binomial coefficients are written like this: n choose 0, n choose 1, n choose 2, and so on, n choose r, and so on. Last is n choose n. And then the term of u. Here first is nth derivative of u, then n minus 1th derivative of u. The derivative of is decreasing, order of the derivative is decreasing of u. First having nth derivative of u, and then n minus 1th derivative of u, then n minus second derivative of u, and so on. Likewise, the last term contains 0th derivative of u, means u only. And next part in each term is of v, function of v. Here no derivative of v, so v as it is. And then first derivative of v, v1, second derivative of v, v2, and so on. In general, rth derivative of v, and finally nth derivative of v. So the order of derivative of v goes on increasing, and the order of derivative of u is being decreased by single term. So this is the statement of Leibniz theorem. And now we shall prove the theorem. We shall prove the theorem by the method, important method of proof, that is the method of mathematical induction. So we shall prove the theorem by the method of mathematical induction. And we see what is the method of mathematical induction. It has two steps. Now the first step is prove the result for n is equal to 1. That is step 1. And what is the second step? The second step in the method of induction is assume the result. Assume the result for n is equal to m. And prove it for n is equal to m plus 1. If you do these two steps, then the theorem or the result is true for every integer n, natural integer n, natural number n. That means n taking value 1, 2, 3, etc. So that method is known as method of induction. It is like a ladder and having different steps. N is equal to 1, 2, etc. And in general, this suppose it is equal to m. N is equal to m. And the next will be n is equal to m plus 1. And further, this is n is equal to m plus 1. And it is continued. Now, who can climb this ladder having these steps? There will be two conditions. One must climb to the first step in the ladder. And the second condition, according to second condition, if one has on this step n is equal to m, then from this step he should go to next step just by one. That is a consecutive step. N is equal to m plus 1. Then using these two steps, one can climb every steps of this ladder. And similar to that, the result will be true for every value of n having natural number. So here n is equal to 1, and from n is equal to 1, one can go to the next step. N is equal to m plus 1, means n is equal to 1 plus 1. Second step, he or she can go to second step. And when he is at second step, by the same step number 2, he can go to next step. N is equal to 2 plus 1, that is 3, and so on. So this is repeated to climb up all the steps. That is the method of mathematical induction. Now we shall consider the two steps separately to prove the theorem. Step 1. For n is equal to, we will prove it for two values. N is equal to 2, 1 and 2. Now we have first n is equal to 1 means first derivative, because n is the order of the derivative, and n is equal to 2 means second derivative. So we shall obtain the first derivative and second derivative of this product u into v. So we have, this is by direct differentiation, first derivative of u into v by the rule of derivative of product. So this is derivative of u, that is u suffix 1 into v as it is, plus u as it is into derivative of v1. And now you see, this can be whether the theorem, this satisfies the theorem statement. This we can write as n, here n is 1, so 1 c 0 or 1 choose 0, u1 v, plus 1 choose 1, 1 c 1, u into v1. And see, this is n is equal to 1. Now if you put n is equal to 1 here, what we will have? 1 choose 0, u1 into v, plus, and what is the next term? N is 1, so 1 choose 1, u, see, what is n minus 1? That is 1 minus 1, and that will be 0. So no derivative of u into v1. And this is the last term, because the last term is n choose n. If these two numbers, suffix and affix, are equal, then that is the last binomial coefficient. So thus there are only two terms in the first derivative, and these are according to the theorem. Or you may check, this last term is 1 choose 1, u v1. So this is the same as this one, and thus this shows that the theorem is true for n is equal to 1. So the first step of induction we have done, but we will also verify for n is equal to 2, or n is equal to 2. So differentiate this first derivative to get the second derivative. So these are binomial coefficients we will use further. Also we have second derivative of u into v. From this, differentiate this. So second derivative will be second derivative of u, derivative of u1 is second derivative of u into v as it is, plus now u1 as it is, derivative of v is v1. This is by the product rule of derivative. So u1 into v, that we have written, u2v plus u1 v1. Now the plus second derivative of this term, u into v1. Derivative of u into v1, we write derivative of u1, v1 as it is, plus now u as it is, derivative of v1, that is v2. And now this can be written as, see, this we have u2v, and I shall write this as 2c0 or 2 choose 0, u2 into v, and plus this is double term, u1 v1 plus u1 u1, that is twice, and I write that as 2 choose 1, 2c1, u1 v1 plus, and this we can write 2 choose 2 2c2 and u into v2. Because why this is so? Because 2c1 is 2, 2 choose 1 is 2, and that is 2 times u1 v1 we have, and we have earlier written 2 choose 0 is 1, 2 choose 2 is 1. So this so therefore now verify whether it follows the theorem, or whether the theorem is true for this number n is equal to 2. That is second derivative of u into v. Put n is equal to 2, and what is the first term? 2c0, 2 choose 0 u to v, plus 2 choose 1 2c1 u1 v1, 2 minus 1 is 1 u1 v1, and next means that is the last, or you can see this 2 choose 2, n is 2, 2 choose 2 u v2, and thus this shows that the theorem is true for n is equal to 2. So we have done this as extra step. Actually only this is sufficient. Theorem is true for n is equal to 1. Now we go to second step of induction. Step 2. Assume the result. Means here the theorem is true for n is equal to m. Yes. Assume the theorem is true for n is equal to m. What is the meaning? Just write in place of n as m, then the theorem is true. So replacing n by m, we write the statement of the theorem. So therefore we have now I shall write this statement in terms of m. Mth derivative of u into v is equal to m choose 0 umv plus m choose 1, or you may read this as mc1 u m minus 1 v1 plus m choose 2 u m minus 2 v2, and so on, plus. But for this we will write a previous term to this. Now you can guess what will be the previous term. Here the binomial coefficients are increasing order of r, and therefore the earlier term to this is n choose r minus 1. So that is n choose r minus 1. And what is this term is u, instead of n we have m. U, or the order of the derivative is m minus, and this is r minus 1. So the difference of these two is the order of the derivative. We are writing previous term, so therefore the difference of these two is the derivative, that is m minus r minus 1. V r minus 1 the derivative of v. That is the earlier term to this, and plus the next term is m, I shall write here, plus mcr, means m choose r. U, the derivative of u is m minus r. M minus r the derivative of u, vr, and plus so on. The final term in terms of m is m choose m. M choose m, u, v m. So what we have written the same statement in terms of m, because we have assumed the theorem is true for n is equal to m. Wherever n is there, we have written m, and one more term we have written extra earlier previous to this term. We have written in terms of m. So you should verify this. And thus this is the mth derivative of u into v. What we have to prove? The theorem remains true for m plus 1th derivative of u into v, and therefore we shall, to get m plus 1th derivative, we shall differentiate this on both sides to get the next order derivative, m plus 1th order derivative we want to obtain. So therefore differentiating this, with respect to x, we get, now you see the derivative of this with respect to x. I shall write here. So this part we have done. So this is our statement of the Leibniz theorem. Now I shall continue this step. M plus 1th derivative. Differentiate this means the derivative order will be increased. That is m plus 1th derivative of u into v is equal to. On the right side, see there are different terms and we have to differentiate each term by using the rule of differentiation. So derivative, we are differentiating this means this derivative will, on left side we have written only in terms of order, next order derivative. Now the derivative of this first term plus derivative of second term plus derivative of third term and so on, we have to differentiate each term on the right side. And while differentiating this first term, you see mc0 is a constant and it remains the same. We have to differentiate this product um into v once using product rule. So we have to use the product rule for this. So I shall write this as m choose 0 as it is, and I write the derivative of um into v in bracket using the product rule. So product rule we shall use like this: derivative of first, second as it is, plus first as it is, derivative of second. So that will be derivative of first means m plus 1th derivative of u, and second as it is, that is v, plus now first as it is means as it is, and derivative of second means v1. So this much is the derivative of the first term, plus go to next term, that will be mc1, and so I shall write here plus m choose 1, and in bracket use now the product rule for this. See, it will be first derivative of minus 1, and that is mth derivative. Order of derivative will be increased. So while writing the derivative, we have to increase the order, and v1 as it is in the product rule, plus now first as it is means minus 1 as it is, and derivative of v1 means v2, and plus the next is m choose 2, mc2, and again the derivative there will be derivative of first means derivative of minus 2, and that means its order will be increased by 1 and it will be m minus 1. So m minus 1 the derivative of u into v2 as it is, plus next is first as it is m minus 2, and derivative of v2 is v3, and this is continued, plus so on, so plus so on, and now plus derivative of this term we shall write, and that is m c r minus 1, m choose r minus 1 in bracket. Now derivative of this, see, this will be m minus r plus 1, and the derivative, the order will be increased by 1. So this order is actually m minus r plus 1. So if you increase the order, then it will be m minus r plus 2, and that is the order of the derivative of u m minus r plus 2, and second as it is v r minus 1, plus now the first as it is which will be m minus r plus 1, this is minus r plus 1, and the derivative of second, that is vr. So this much is the derivative of this term, and plus the next term is in continuation m choose r, and now the derivative of this product. So it is you can verify using the same rule we are using, product rule we are using to write the derivative of each product. So it is u m minus r plus 1, derivative of first, Vr as it is, plus first as it is means u m minus r as it is, derivative of Vr is Vr plus 1, and this is continued plus, and finally what we have is m choose m, and in bracket the derivative of u into Vm, that will be derivative of u is u1 Vm as it is, second as it is, plus now the first as it is u, derivative of Vm is Vm plus 1, order is inverse. So thus we have differentiated the right side, taking derivative of each term using the product rule. So you should verify this. Now this we shall simplify. Now while simplifying this, we note that this is left side is m plus 1th derivative of u into v. Now observe this. So the terms we should observe, and this is the term m choose 0 as it is, u m plus 1 v, and next, so I shall write this term first, separate term, m choose 0 u m plus 1, m plus 1 the derivative of u into v, plus, now we may observe this term and this term is the same. So we shall take this term common and write their binomial coefficients in bracket. So what is the binomial coefficient of um into v? That is m choose 0. And what is here binomial coefficient of the same term? M choose 1. So that is common. So in bracket I shall write m choose 0 plus m choose 1. And the term is, so this term further will be, so I shall write as, see, m choose 0 plus m choose 1 is common, and um means mth derivative of u v1 plus, now the next you see these two terms u m minus 1 v2 and again u m minus 1 v2 is the same. So therefore again take this term common and write their coefficients in bracket. So m choose 1, that is m choose 1 plus m choose 2, and in bracket it is m minus 1th derivative of u into v2, and so on. Further this is continued plus so on, plus dot dot so on, and now we shall see these two brackets further. So this is continued plus so on, plus now from these two general terms you observe this is common, u m minus r plus 1 and vr, u m minus r plus 1 into vr is common. So in bracket these two terms will be there, that is m choose r minus 1 plus m choose r is common, and what remains outside this bracket is this term u m minus r plus 1 derivative into vr. So thus we have written the general term here, and finally we write the last term only, this term. This will be grouped with the previous term, and so therefore last term and the first term is single. So this is first term and this is the last term. So these are separate terms, and last term plus so on, I shall write this as m choose m choose m, and u into, this is m choose m and u into vm plus 1. So thus we have expressed the right side in this form, taking terms common. terms having the coefficients are taken in bracket, and this is the common term. v1 is common. Here further next minus 1 v2 is common, and so on. So we have written this. Now we shall simplify these brackets using the binomial coefficients, results on binomial coefficient, and then we rewrite this. So now these two results are the same, so I shall rub out this and continue writing here. This is further equal to m plus 1th derivative of u into v is equal to m choose 0 is actually 1, and see, we are going to use this m choose 0 is same as m plus 1 choose 0 is same as n choose 0, all are equal to 1, and also this is equal to m choose m, or this is also equal to m plus 1 choose m plus 1. So these values are equal to 1, and therefore the first term I shall write m plus 1 choose 0, because these two are the same, and next plus into m plus 1th derivative of u into v plus. Now what about this? This result we have written earlier, that is m choose r minus 1 plus m choose r, and this addition is m plus 1, that is the affix is increased by 1, choose r, it is r. So this is the result. These two results we are going to use in this simplification. So what will be this value? M choose 0 plus m choose 1, that will be m plus 1 choose 1. So it is of this form: m choose r minus 1 plus m choose r. Here it is r, here it is r minus 1. One term less than this one. Here it is 1, here it is 0, and the affix is the same. So this sum is by this m plus 1, r is here 1. So increase the affix by 1 and take the suffix here as the same, and therefore this bracket is m plus 1 c1 by this second result. So we are using this. Earlier we have revised this, the same results we are using, and therefore m plus 1 choose 1 u m into v1. Now what will be this by the same result? M choose 1 plus m choose 2. This will be m plus 1 choose 2, this number, see, second, and therefore this is m plus 1 choose 2, and it is m minus 1th derivative of u v2, and so on, plus so on, plus. Now what is the general term? It is the same, m choose r minus 1 plus m choose r, and it is exactly m plus 1 choose r, and this I shall write u in terms of difference of these two, and I shall write u m plus 1 minus r. It is the same, m plus 1 is written first, minus r, and vr into vr, plus it is continued, and final term I shall write m choose m, but m choose m is same as m plus 1 choose m plus 1. So the final term I shall write m plus 1 choose m plus 1, and this as it is u into m plus 1 derivative of u. So thus we have simplified this step in this form using these results from binomial coefficients. Now you should verify. We have used, here we have simplified, first we have used product rule, then we have taken the terms, common terms together, and then we are using the binomial coefficients results. So you should note this result, and using these results each bracket is simplified. The first is written in terms of m plus 1 C 0 or m plus 1 choose 0, and the last is written as m plus 1 choose m plus 1, like this. So thus, now you should observe. We should observe this result and the original theorem. Now whether the theorem is true for n is equal to m plus 1, that we have to verify. Now replace here n by m plus 1 and check whether we get the same terms as like this. So replace n by m plus 1, m plus 1 the derivative of u into v, m plus 1 choose 0, u m plus 1, m plus 1 the derivative of u, v as it is, m plus 1 choose 1, m plus 1 minus 1, that is m, here v1 as it is, m plus 1 choose 2, and m plus 1 minus 2 means m minus 1, here it is we have to write m plus 1 minus 2, that is m minus 1 v2, and so on. See the general term, m plus 1 C R means m plus 1 choose R, and here it is replace n by m plus 1, m u suffix m plus 1 minus R, VR, and finally replace n by m plus 1, m plus 1 choose m plus 1, u v m plus 1. So this shows that the theorem is true for n is equal to m plus 1. So thus we have obtained the second step. So we can write, this shows that the theorem means this result is true for n is equal to m plus 1. So thus in the second step of the method of induction, we have assumed the result is, or the theorem is true for n is equal to m, and we have proved the same theorem remains true for n is equal to m plus 1, and that is the second step in the induction. And thus the theorem will be true for every integer, positive integer value of m. And now we can write the conclusion here as, by step 1 the theorem is true for n is equal to 1 and 2. And now apply the step number 2 for this in continuation. So by step 2 the theorem is true. Theorem is true for n is equal to m plus 1. Now we can take the value of n as 2. So it is true for 1 and 2. We shall consider now m is equal to 2. So 2 plus 1. The theorem is true for 2 plus 1. When it is true for 2, it is true for next value, next immediate value, that is 2 plus 1. So it is equal to 3. And further, continuing like this, it is true for n is equal to 3 plus 1, that is equal to 4, and n is equal to 4 plus 1, that is equal to 5, and so on. So thus the theorem is true for, thus by the method of induction. This is the method of induction that we have used, and therefore by the method of mathematical induction the theorem is true for n is equal to, starting with 1, 2, 3, 4 and so on, infinite number of values are all natural numbers. The theorem is true, and this completes the proof of the theorem. So n is a natural number or positive integer then we can get the nth derivative of the product of u into v. So this completes the proof. And in this way we have proved the Leibniz theorem. So you should go, this is an important theorem, you should go through the steps of the theorem in the proof we have used. We have used the binomial coefficients, results on binomial coefficients, and only we have used the product rule. And two steps are there in the method of induction that we have used. And by step 1 and 2, the theorem remains true for every positive integer, n is equal to 1, 2, 3, etc. So this completes the proof. The problems on this Leibniz theorem we will consider in the next lecture. Thank you.